If we just summarise where we got to last time, we have Isaac Newton with his corpuscular theory, all right, with light as little, I think, vibrating particles, okay, and we have the theory of Christian Huygens, which is the idea of the wave, okay. We talked last time about the fact that what you need is a sort of pivotal or a crucial experiment that will prove one or the other wrong, and of course the problem is a lot of the common properties of light don't do that. Reflection, refraction, they all work fine with both theories. You need things like interference as the crucial experiment, and it's worth, I think, just putting in some of the dates, which will explain to you, I think, what it says in your spec about why the correct theory wasn't accepted for quite a long time. Okay, Isaac Newton died in 1727. Okay, Huygens around about, I think, 1695. So Huygens is actually a predecessor of Newton. And this experiment to demonstrate the interference of light, as you know, is the famous Young's two slits experiment, which actually dates from 1801. So the first practical demonstration of the interference of light, the fact that you can use light to create bright fringes and dark fringes, you can see the dates there. Okay, in the case of Huygens, there's the theory, but there's the first experiment that proves that actually that's wrong and that's right. So you have essentially, and of course in this period here, after Huygens died and Newton was around, Newton continued to work to a grand old age and was very high up in the scientific establishment, president of the Royal Society, all that sort of stuff. So in this period here, obviously Newton's theory prevailed, partly because there's no experiment at the time that could prove between the two, okay? And secondly, Newton's status, okay? And then, after Newton dies, of course, it just continues, all right? After Newton died, people have been teaching Newton's laws of motion, well, because they're right, obviously for hundreds of years, and the corpuscular theory kind of did that. If you went to school in this period, you would have been taught Newton's corpuscular theory, not because there was direct practical proof of it, but because Newton got so much other stuff right, gravity, laws of motion, all those sorts of things, and many other areas of optics as well. And it's not till 1801, Thomas Young's experiment, that proves the wave theory. Okay, so that's the bit in your syllabus about why the correct theory. I think they use the phrase delayed acceptance, and you can see why. If you put the dates in, it kind of makes sense. Okay, but it's an unusual piece of physics where the theory and the experiment are out by quite a long time. In the case of Huygens, over 100 years. Okay. We are going to have a quick look at Young's double slits. I'm conscious you did it in year 12, and we're not going to go through the equations and stuff like that, because that's not required for turning points. But you need to have the idea that if you want to take two sources of light, or something like that, you need to get your light waves coming out, and you need them to overlap, and here you'll get some sort of interference pattern. You'll get places where the waves arrive in phase and produce brighter waves, and you'll get places where the waves arrive exactly anti-phase and produce darkness. Okay. Now to do that, the key thing here is to understand the problem. All right. It's not too difficult to get two sources of light, shine them onto the table in front of you, and there will be an interference pattern. Okay. The problem is the two sources are obviously independent, so the interference they form, pattern will form there, and then 1/2 a wave later, there'll be a slightly different pattern. So there is, if you like, from the two strip lights in this room, there's an interference pattern forming on your table in front of you, but the trouble is it's changing with every successive wave of light. Now light has a frequency of like 10 to the 14 hertz, so every 10 to the minus 14 of a second, the interference pattern on the table in front of you is changing, which means you can't see it, okay? So the problem with this interference pattern is not forming it, all right? On the table in front of you, there are little dark patches where two light waves have cancelled each other out, but it's gone. It's gone in such a short time. The problem is making this stable in terms of time. This is the problem with doing interference of light, is you need to get the pattern to stay there for long enough for you to see it, which means whatever the phase relationship between these two sources, it must remain stable over a period of time. Okay? The waves can arrive in phase and produce a bright spot. They can arrive out of phase and produce a dark spot. But unless that continues, unless every successive wave is in phase or every successive wave is out of phase, you're not going to get a pattern that lasts for long enough. Okay? So it's important to understand exactly what the problem is here. It's a problem of keeping the waves with a constant phase difference. Either in phase or out of phase doesn't matter, but they must stay. Not just for one wave, the next one and the next one and the next one, they must all have the same phase relationship. Okay? So if you think about it quickly, you might say, well, you've got to get the waves to arrive in phase, you've got to get them to arrive out of phase. That's not the problem. However you get them to arrive relative to each other, it's got to stay like that, not just for one wave, but for the next one, and so on. Okay? And the name we give to this property of having a fixed phase relationship is we say, change that, we say they are coherent. All right? Very, very important term. If I'm an examiner, I'm going to be picking up on something like that. Does the candidate understand the crucial piece of physics? Not just remembering the bits and bobs of Young's experiment. There's no marks in drawing that, because that's just recalled. Coherence, all right? Coherence is the phase relationship staying constant, all right, not changing with time, which means one pattern will be the same as the next one, and then you get something that you can see, okay? So first thing to remember about Young's double slits, if this is revision for you, is coherence. And be very clear. You sometimes see exam questions where I ask to explain what's meant by coherence, because it's so easy to muddle it up with being in phase or out of phase. It doesn't mean any kind of phase. It means whatever phase relationship you've got, it's staying the same. It's not changing. Okay? Now, in simple terms, let's just go very quickly through how Young did his experiment. He would have had some sort of source of light. I'm fairly confident he wouldn't have had an electric light. He would have had something, okay, to produce some light. And the first thing he did was to use a bit of diffraction. So he sends the light through a single slit, okay? And that obviously diffracts the light waves so that they basically start to behave as though they've come from a single source, which, as you know, means that you get spherical waves, okay? And then he allows them to hit the famous double slits, okay? So two slits in a piece of metal, gaps in a piece of metal or something, very close together. And what's going to happen now, of course, is the waves will hit that and they'll start to diffract out again. So the waves from that one will look like that. The wave from that one, again, they'll behave as though they're sort of spherical waves. And here, they'll start to overlap. Okay? And then, if you put a screen here, I think what he did was actually to have a screen and then have a microscope, because the fringes will be very close together. A microscope you can move up and down, and then, obviously looking in there, okay? You would get your fringes, all right? So on this screen here, you would get this kind of pattern of light and dark, alternating fringes, okay? Roughly equally spaced, but again, that's not something they're going to examine in the turning points. The point is you get points of constructive interference, where the waves are supporting each other, and you get points of destructive interference, where the waves are cancelling each other out, okay? And, very importantly, because the waves are coherent, this pattern stays there for long enough for you to look at it, okay? You can see it's going to be very dim, firstly because early 19th century light sources were not very powerful. First of all, how much of that light energy that's all going out all over the place, how much of that light energy do you lose in the first slit? Loads and loads of it. Of the energy that gets through, how much light do you lose in the second, in the double slit? Loads and loads of it. So by the time it gets here, it's going to be really, really faint, okay? So there would have been very, very faint fringes, okay? In the 20th century, or sorry, in the later half of the 19th century, the way you could get around this would be to put photographic film there, like old wet chemical photographic film, and just leave it there for a long time, so that gradually you record an image of the fringes, leave it there, for several hours to pick up the information, and then develop it, and you've got a photograph. But of course, in this time, remember the date? So you remember 1801. You just had to sit there, probably sit there for half an hour to let your eyes accustom to the darkness in a darkened room, and then very carefully look at this microscope, just move down, and you can see the fringes. Okay, but very importantly, this is the first practical demonstration of the wave theory. Okay, this is the crucial experiment, which happened long after Huygens was dead and long after Newton was dead. Okay, so we do have this period where the corpuscular theory, quite a long time, for nearly a century or so, or just under 75 years or so, the corpuscular theory was accepted. Okay.